Okay, welcome back for the last seminar of this beautiful week. We are gonna finish with Jahanur Hoque from ULB Brussels. He's gonna debate for us and with us the quadrupole formula and the sitter.
Between us.
Between us. Thank you.
Okay, so I will talk about debate on quadrupole formula in de Sitter. So at first, I will try to convey you why there was a debate, and I will also prescribe some possible resolution for the debate. Okay, so let's start with some really basic stuff. So as all of we know, one of the crucial prediction of GR is that there's the existence of gravitational waves, which you can think of as the ripple on the space-time fabric. And 2 years later, Einstein also derived his celebrated quadrupole formula, which basically says if you have some gravitating object, then it estimates how much power it radiates actually to the null infinity. And you can write this energy loss formula in terms of triple derivative of quadrupole moments of the system. So if I have system, say gravitating object, I can just compute what is the quadrupole moment for that object, then I just take the triple derivative. So this is also analogous to if you just understand the Maxwell field theory, where the field depends on the dipole moment to the leading order, but in GR actually it depends on the leading order to the quadrupole moment. And also Einstein relates this linearized field Hij in terms of quadrupole moment. So what you do, you just write down the wave equation for linearized field and try to solve this in terms of retarded Green's function. Once you solve that, then you can show that this d3x Tij integral you can write in terms of double derivative of quadrupole moment. So this you can from this step to this step, you have to use only the conservation equation. You just use del mu T mu nu equals to 0, and just do some integral by parts and assume that your source is compactly supported. Then you throw some boundary term, then you will get this formula actually. Okay, so this is completely basic GR stuff. And then, as I said, Einstein analysis actually are done. This analysis is done in linearized context, and also you have to choose a gauge, namely harmonic gauge or de Dondar gauge. It is analogous to solving Maxwell equation in Lorentz gauge. And then after that, there remains a confusion over the years for whether gravitational waves actually exist in the full nonlinear theory or not. So Einstein gave this formula in 1915, and you can see the timeline. This is settled by Bondi in 1962. So there's a long debate whether this gravitational wave really exists in nonlinear theory or not. And Bondi and his collaborator actually provided a detailed full analysis of gravitational wave in nonlinear theory along with mass loss formula. So this mass loss formula is also important, which basically says that if you have, again, a gravitating system in the asymptotically flat space-time, you can just ask what is the energy loss by the system, and you can just compute from this formula. So this CAB is nothing but a shear. So it's just 1/r part of your sphere data. And you can just compute this del U CAB, which is news, integrated over square. So then this R square exactly cancels. And also, you can relate this CAB in terms of previously what I said in terms of Qij. So this correspondence is also 1-to-1. So I can just do a coordinate transformation from Bondi gauge to this harmonic gauge. Then I can show that this CAB is exactly nothing but Qij double dot. Okay. So now, what happens? These two lines of studies are important, obviously, in different contexts. Namely, Bondi-Sachs analysis is important to analysis of gravitational wave in asymptotic analysis, asymptotic symmetries, understanding gravitational memory effect. And also, harmonic gauge is important to understand the source dynamics, actually. If you want to solve the far field, far region of the field, and in terms of source moments, then harmonic gauge condition is actually very much important. And it has a lot of application in terms of, say, gravitational wave generation and data analysis. So such that if LIGO says, so from the data, we just infer, say, some mass of the black hole or the spin of the black hole, actually that goes through this formalism. You have to do this harmonic gauge or de Dondar gauge analysis, okay? Now, moving to the next slide, now let's ask what happens if we just turn on the cosmological constant, because the cosmological observation suggests that our universe is undergoing accelerated expansion, and this is most simply modeled by a de Sitter universe. Now you can ask all these sort of questions what I showed in the previous slide in terms of de Sitter context, okay? In particular, you can ask what are the flux balance formula for de Sitter isometries. So I can have a de Sitter background, then I have de Sitter isometries, then I can ask what are my conserved charges and fluxes for these isometries. And can I write down a quadrupole formula for gravitational radiation in de Sitter? And how to generalize Bondi-Sachs formalism for de Sitter? And is there a negative definite energy flux, as I showed here? So this carries a negative definite sign. So that means the system is losing its energy. And similarly here also, there's a negative definite sign, okay? Now, if you ask this question, so, and the answer is all these questions are very non-trivial. And it took almost 100 years to make at least an attempt to generalize Einstein quadrupole formula. It started by a series of work of Abhay Astekar, Beatrice Bonga, and Aruna Keshavan. And also it is part of my PhD work also. And I will try to convey you that there is still a confusion. So, and on 2023, we wrote a paper saying that what do you mean by exactly quadrupole truncation in de Sitter? And you have to be really careful by what do you mean by quadrupolar order in de Sitter. So this is will be the part of my talk. And then, so let me just make this comment. Then all the analysis for lambda equals to 0 case actually doesn't go through for lambda non-zero case. And one of the reason is that if we just turn on the cosmological constant, your global structure of the space-time changes immediately. And it is a just consequence of Einstein equation, nothing else. So you just look for the conformal Einstein equation and just ask what is the norm of the normal of the boundary. Then you can see the norm of the normal actually depends on the cosmological constant. So if you set lambda equals to 0, it is null. If lambda greater than 0, it is time-like, ADS. If lambda greater than 0, it is time-like, it is a DS. If lambda less than 0, it is ADS. Okay. Now, to get into details, so I will concentrate on DS4. And de Sitter spacetime can be think of as a hyperboloid embedded in a 5-dimensional Minkowski spacetime. And this is a Penrose diagram of the full de Sitter spacetime. This is chi minus, this is chi plus. And in this global coordinate, de Sitter metric looks like this. And you can see this is this has a on the boundary, it has a S3 topology. So this is chi plus. So chi plus of full de Sitter is S3. But for all of the purpose of my talk, I will just assume there is a source near this line AD. So that means this source can affect only this upper part of the de Sitter spacetime. So for all purpose of my talk, I will just concentrate on the future Poincare patch of the de Sitter. Okay, because if I have a radiating source here, so it causally it cannot affect this part of the spacetime. Okay, now let's look at. As I said, we want to understand the flux balance law of de Sitter background isometries. So let's look at the holographic stress tensor of de Sitter. So as Marika also mentioned, so the future region of de Sitter actually has an expansion like Starobinsky expansion. So you can just expand like this. And you can see if you just conformally compactify this space-time with respect to your conformal factor tau, then you can see your boundary metric is this G0. So you just rescale this metric and take omega goes to 0, which is the definition of the boundary. Then you will get G0. And also you can identify GAB3 in terms of TAB. Also this GAB3 actually you can write in terms of electric part of while. And for the Pfefferman-Graham gauge, you can relate G0 also in terms of GAB2, and GAB1 is explicitly 0 by Einstein equation. So then this TAB actually also satisfy this divergence-less condition. So this DA0 is with respect to background. So stress energy tensor actually satisfies divergence-less condition and stresslessness condition. So this is just a consequence of Einstein equation. So this is just, I think, the usual Starobinsky expansion or Pfefferman-Graham expansion. So I'm not assuming anything. So I'm just assuming that de Sitter actually allows near Scry this kind of expansion. Yes, and also I think it goes to the, there is, I mean, it should be, the space-time should be smoothly conformally compactified. So, I mean, I think it is also a consequence of Einstein equation that the log term cannot be here.
With conformal anomalies, you'd have to have, if you had scalars of particular dimensions, particular masses, you could get log terms. But here implicitly, he's just solving Einstein's equations just with a positive cosmological constant, and this just follows from the solution of the equations.
Yeah,
Einstein equation, no matter.
No matter. This is just Einstein equation. Yes.
Yeah, it's empty.
Okay, now as we have stress energy tensor, now let's ask what can I understand of flux balance law from this TAB. So for, say, for any arbitrary vector field xi A, so this identity should hold because my TAB is divergenceless and traceless. So this is divergenceless and traceless. So this only contributes to the symmetric and traceless part of xi. Because if I act D on TAB, it is 0. It will act on xi. So, but it contains only symmetric and traceless part because my TAB itself is symmetric and traceless. Okay. Now let's assume that our background has a conformal Killing vector, say xi A bar. So if I assume that, then this equation is satisfied because my background Killing vector. Then look at the linearized perturbation of this equation actually. And for all of my talk, I will look at the linearized theory. Okay. So if you just try to perturb this one in a linear theory, then you'll get the contribution from. So this term is exactly 0 because if I take the delta TAB, so this is background. So then it's satisfied by the conformal Killing vector. So this term is exactly 0. Then from here, you will get two term. So if you just assume that you have some boundary of S1 and S2, so then you will just get a charge on S1 and the other one should be S2 minus S2.
I have a question.
Yeah.
What is M and what is U in the first equation?
Which one?
What is M, the integration region?
Ah,
What is U, the coordinate?
Okay, so M is, you can take off this full region, and this one is S1 and S2. By U, actually, we mean that, yes, so this slice, by U, we mean we have a, in mind, actually, we just want to go to the in the boundary coordinate, actually. In the later part of my slide, it will be more actually clear. Because, I mean, yeah, so we have in mind that we want to do it for boundary coordinate, then we just go from here to boundary coordinate, actually. That's why we just... I just write it in terms of U. So then you can see this charge is conserved linearly. But if you want to take the quadratic variation of this equation, then it is not conserved. Because if I take the quadratic variation of this, so there is a quadratic variation from this TAB, because from this, for this equation, this is automatically satisfied. And you can write down this total derivative in terms of a integral only on the boundary of this two boundary, and this contributes from this term, and this term will contribute to two terms. So one is delta T of this one and delta of this one, because for the background, this is again 0. Okay, so this is actually quadratic, but quadratic in the linear field. So if I have linearized theory, then the energy loss actually comes to the quadratic level. So that's why this linearized that's why it is not conserved actually. So in the linearized theory, as the energy appears in the quadratic level, that's why this charge is not conserved. Okay. Now, yeah, so this is the definition of our charge. I think it is also showed by Marika. And then this is our flux formula, because we just define this charge. Then from this equation, so this is our flux formula. This is our flux. So this is the difference between the charges in two cards, and this is exactly the flux. Okay, so that's why we defined here this one. Now, what we want to do, we want to understand this formula in the context of Bondi-Sachs formalism, because Bondi-Sachs formalism actually is very well understood by now in de Sitter framework. I mean, it is started by some work with Marika, Skanderis, and Pole, where they define in terms of axisymmetric case. Then Geoffrey et al. Generalized it in terms of all these non-axisymmetric case. Then also we wrote a paper saying that how to interpret energy in terms of symplectic structure. Then last 2023, Bonga Boonstar Perez also wrote a paper, and then also Gaylor has a paper. So this has a really developing field, and it is just going like a very interesting way. Okay, now this is the pictorial diagram, what physical picture I have in mind. So you just define a charge on two cards, then the flux is associated with this leakage, which I described here on this one. And we want to understand this quantity in terms of Bondi-Sachs formalism. That's my goal. So now let's introduce Bondi-Sachs frame indicitor. So Bondi-Sachs frame are based on outgoing null hypersurface, such that U equals to constant lines are null. So once you have this setup of this coordinate, then immediately the consequence is that GUU up is 0. And also to claim that your theta phi coordinate are orthogonal to U direction. So again, this translates into GUA up is 0. And then I want to write down my metric in a covariant fashion. So you just use this identity. Then you can show immediately that GRR down and GRA down is 0 in Bondi-Sachs coordinates. So if I choose my outgoing null hypersurface, immediately the consequence is that your metric cannot have GRR and GRA component. Okay, so this is the usual Bondi-Sachs coordinate. Now let's look at what happens to the de Sitter background metric in Bondi-Sachs coordinate, because I will restrict to all my analysis in linearized field. So I will consider the field on de Sitter background. So this is my background metric. So I'll just consider my full field G as some G bar, which is de Sitter background plus H. Okay. Now I'm writing this G bar in terms of this Bondi metric. So once you write G bar in terms of Bondi metric and you put R equals to 0 here, then you immediately restrict yourself on this upper half. You can show Bondi coordinates actually goes only in the upper half, upper panel of the de Sitter. So once you fix your time-like source here and fix to R equals to 0 Bondi coordinate, then you restrict yourself only the upper half of the de Sitter metric. And you can also see the background metric in DS coordinate looks like this one. Again, similarly, you just do a conformal compactification, say that R equals to 1 over omega, then look at the unphysical metric and take omega goes to 0 limit. Then you will see this GAB0 is your exactly background metric actually. Now we want to understand what is the symmetries of the background metric, okay? So if you just ask that question, then immediately you will see this background metric actually satisfy the conformal killing equation. So as it satisfies the conformal killing equation, and the solution of this conformal killing equation are this 10. Because I'm in the de Sitter background, so I expect I have a 10 isometric group, so it exactly identifies SO1, 4 isometric group of de Sitter. So I'm just asking what are the solution for this conformal killing equation, okay? Now, in linear theory, I will ask what are the associated symmetry with this background, what are the associated charges and flux for this conformal symmetric vector, okay? That, I mean, that is the usual strategy to understand the linear flux in linearized theory, and any charges or fluxes. So, okay. Now let me give you a brief review of Bondi-Sachs formalism in de Sitter, because it is really non-trivial, and I think it is worthy to make some comment on that. So in de Sitter, actually you can just give me some data, sphere data. So all this is my delta means the linearized field. So give me the linearized data on the sphere, this one, and Bondi equation actually gives you this fall off. So these are the consequence of Einstein equation itself. So give me a data, delta GAB, then Einstein equation will tell you what is the delta GUA, delta GUU, delta GUR. And the non-trivial part is that this delta UA0 and delta UA0 here. And this delta NA can be think of the mass aspect in terms of asymptotically flat space-time, and M can be think of mass in asymptotically flat space-time. And also, Einstein equation provide some evolution equation for mass aspect and angular moment aspect. So this is one part of Einstein equation which says hypersurface equation, namely, if I just fix on a hypersurface, so give me a data of GAB, I will write down the other solution on this particular hypersurface. And the other set of Einstein equation actually says, how can I evolve this equation along the del del U? So that will give you some evolution equation along the null cone. Okay. So once you have that, okay. So, but let me emphasize one of this one non-trivial equation in de Sitter. So this is just a consequence of Einstein equation. You just look for the Einstein tensor, but in the angular part of the Einstein equation. So the leading order term of this equation will give you this constraint. So which says you, if you just take delta U of QAB is related to h square of shear plus with this combination. And the interesting thing is that in lambda equals to 0 limit, you can put this term as a completely a gauge term. In lambda equals to 0 case, I can just, this term is not there. So I can put delta QAB and delta UA is a completely a gauge. But you cannot do it for de Sitter. So if you want your space-time has some dynamics, then you cannot turn off delta Q or delta UA to be 0 simultaneously. But I mean, this is really a non-trivial equation for de Sitter. Okay. So what I mean, so if you look at again this expansion, so the leading term is delta QAB and delta UA. So in flat space, actually I can turn off these two terms simultaneously by a gauge transformation. But in de Sitter, you cannot do that if you want some dynamics to your space-time because of this equation itself. Because this equation is exactly trivial on flat space. And this EAB analysis also gives one interesting equation, which is really interesting. I didn't show that. So this gives one equation like lambda by 3 delta of DAB equals to 0. And this is also part of Einstein equation, actually. And if you look at this equation is also trivial for lambda equals to 0 case. For lambda equals 0 case, it doesn't gives you any constraint, but this constraint is actually interesting. So if you look at this answers, so this DAB term is actually explicitly 0 in de Sitter by equation of motion itself. But for lambda equals to 0 case, you cannot say anything. And this DAB term actually produces log term in the further expansion in lambda equals to 0 case. And that's why de Sitter is logarithmically free even in Bondi sacks by equation of motion itself. Okay, but this is not true for lambda equals to 0 case. Okay. Now, once I have all this follow-up condition, then as I said, I can either choose this delta Q AB term to be 0 or delta UA term to be 0, but not both of them simultaneously. So in the literature, actually, there are two kind of boundary gauge fixing. So one by Geoffrey, Fiorucci, and Ruggiconi. What they did, they put this delta UA term to be 0. So I can just put delta UA term to be 0. But I can just say that my delta determinant of QAB is some function of U and theta phi. This is like generalized BMS. So this is like generalized BMS, and they also understand what is the asymptotic structure of the group. It is not exactly group, so they call it a groupoid. But you can understand what are the asymptotic symmetries with this boundary gauge fixing. Again, you can do this boundary gauge fixing actually. So I can just put delta QAB to be 0, but delta UA to be non-zero. But I can choose determinant of QAB as a sphere metric, just like what Bondi and his collaborator previously did. You have a question? Yes.
You can say your own.
About the nomenclature. When you say constraint, you mean like a condition or something, right? It's not like a constraint equation.
This one?
Yeah.
This is just a consequence of Einstein equation. So
no, I mean, when we say constraint equation, that typically means there is no explicit dependence on the time. You don't mean that, right?
Oh, I don't mean that.
Okay,
I
it's just
mean
like a condition or restriction.
Yes, it's just restriction.
Okay.
It is just consequence of Einstein equation.
Yeah, okay, yeah.
So you give me Einstein equation, then I do the leading order expansion, then that just give me this one, nothing else. Okay. Okay. Now, okay, this gauge condition actually we explore, this boundary gauge condition we explore with Piotr Krushel. And but in the linearized context, but Bonga, Bunster, Perez also explored this gauge condition, but in the full nonlinear theory. Okay. Okay. Now, so I set up my Bondi Sachs coordinate. Now previously I mentioned I want to understand this flux balance formula of from this holographic stress tensor in terms of Bondi variable. Now, you can do it in terms of say I can do a coordinate transformation between Graham gauge to Bondi gauge. So this computation is really a bit involved. Then I can write down this flux formula which I have previously shown in terms of this holographic stress energy tensor here, here, here. But I can write down this flux formula in terms of Bondi variable. Just do a coordinate transformation. Yeah, here. And this delta GAB actually depends on the Bondi field. So the details is not that much important. But okay, so this also from this conservation of holographic stress energy tensor, I can also write the analogous formula for mass loss formula, just like Bondi's mass loss formula, the consequence of RUU equation, and you can show you can also derive from this formula actually. So you give me this formula, and I will just restrict for my xi, which is del del u. Then it will give me this formula also, Bondi's mass loss formula.
So, have you, just out of curiosity, check in the sitter whether this diffeomorphism from Pfefferman-Graham to Bondi Sachs is large? In 3D with Mark Geller, we found last year that the usual diffeo that people do from Pfefferman-Graham to Bondi Sachs in ADS is actually large. So it's changing some of the charges. It's
Yes,
a bit
it's
subtle
fine.
to compare the expression of the charges in the two gauges. It's not impossible because, I mean, it's large, but it's physical, so you control it.
Large,
But do you know whether it's large?
Yeah, large, I think in the sense you can actually, you can put this two quantity free also, right? Then my expression, I mean, what I have shown here, it is explicitly in this gauge. So even if when I go from Pfefferman-Graham to Bondi gauge, so I just restrict to this gauge actually. I mean, in principle, you can free this quantity. You can just put all this thing to be non-zero and just look for what are my charges or the fluxes. I think it is large in that sense. So it is paper by Mark, right? It is the paper by Mark you are talking about, Mark Geller.
Oh no! So we did it together with Mark last year, but in 3D. So we don't know in 4D. It's very hard to check. I mean,
But I mean,
that was
I mean, that is the one of the reason actually we choose this boundary gauge fixing to just at least get some mass loss formula. I mean, you can write down a mass loss formula just taking both to be non-zero, but I think it is really complicated. That expression is. Okay, now this is the exactly the flux formula, but written in terms of Bondi variables. But you can show this formula also gives you this mass loss formula of from the Bondi Sachs analysis. So you just look at the RUU part, the Bondi Sachs equation, so that give you some evolution equation of the mass. And also, and this mass loss formula is actually computed in this gauge, in this boundary gauge fixing. But also I can compute the mass loss formula in this boundary gauge fixing. So that expression is also here. But if you don't want to call it mass, so I have at least justification for this actually. So if you look at the Einstein equation, then look at what is the quadratic variation of the Einstein equation from here. And you can look at what is the symplectic structure on the null cone. So give me the Einstein equation, I will just compute what is the symplectic structure on this null cone. Then you can show this quadratic variation of del square m is related to half of the energy you compute on this null cone. So I can compute this energy like I can just compute what is the symplectic structure on here. And I mean, at least in this gauge, we have justified that at least this quadratic variation of m can be related to the symplectic structure on the null cone. Okay, so at least in this gauge, we have justified that. But if you don't want to call it mass also, okay, it is still an identity. You just take it as an identity. So this is just a consequence of Einstein equation, nothing else.
I have another maybe stupid question, but so here, just to make sure, in which of the two boundary conditions you were?
So the first one is I have chosen this this boundary condition, this one.
Okay.
Delta UA to be 0, and the next one I have choose this boundary condition.
Okay.
So namely, this one. So for this delta QAB is 0, and for this delta UA is 0.
And so there's no chi in the first one?
No, there is no chi. I think we fixed here determinant also. So I think here, you mean here, right? L. So yeah, so it should come, it should have some expression of L, but I think chi, we took just determinant of this one.
Ah, okay. So
Okay,
you fixed
yeah,
it even more.
yeah.
Okay, okay.
In
So
principle, there should be some expression of, I think, this
so it's the
determinant
peer
L.
now.
Yes, yes. it
Ah,
was
okay,
pure.
okay. Thank
But
you.
we are, because it is just on the background metric. So because we are in the linearized regime, I can just compute
I
as
understand.
QAB as QAB naught, and that's all the terms in terms of delta
I understand now.
Okay.
Thank you. Thanks.
Okay. Okay, now if you look at this formula, so a priori this formula is not negative definite at all, but it has this two formula exactly has exactly same flat limit. So if you just h goes to 0, h square is lambda by 3, so this term will turn off, this term will turn off, this is like nu square. Again for this quantity, so as I said, this term is 0 for lambda goes to 0 limit, because I can just put a gauge from this equation. So if I have this one is 0, then I can put a gauge. So this term is not there, so I can just put a gauge. This term is automatically 0 for lambda goes to 0 limit. Okay. So for lambda equals to 0 limit, this term is not there. But this two formula even doesn't tell you whether this quantity is positive definite or not, or this quantity is or mass loss is negative definite or not. This doesn't tell you anything. So then what is the puzzle? So a priori, negative definite energy loss formula is not obvious from the any of this mass loss formula on the both boundary gauge fixing. And basically, we don't know how to impose no incoming radiation condition in this de Sitter in boundary size variable. So what I mean, so de Sitter has this full de Sitter. Then a priori, so these del del U vectors are actually space-like here. So if I look for the energy, so this part is space-like, and this part is time-like, and this part is null. So if you look at the background killing vector, okay. So if something, the energy comes from only the left panel, I expect the energy should be positive definite, because nothing is coming from this panel. So I can just restrict all my source here. Then I can expect what I will get from here, something positive definite, or my energy flux formula can be explicitly negative definite. Well, how can I do that? Well, we have an way out. So go to the conformal coordinate of de Sitter and impose this harmonic gauge condition, where we have the solution of field in terms of this source moments. So Abhay and one of my PhD work also. So what we did, so we write down the solution of Hij in terms of this moment of the source. Say the source is in this region, and you can write down the field equation in terms of moment. At least those solution has some information that it uses the retarded Green's function solution. That is that might be a way out. And also, at least previous computations show there is a negative definite energy flux formula in terms of moments in de Sitter. So this is work by Abhay and one of my PhD work. And okay, so let's go into the conformal coordinate of de Sitter. So this in the conformal coordinate, de Sitter background metric looks like exactly this. It is exactly conformally flat in terms of eta r theta phi coordinate. So this is eta equals to 0 is your boundary. So this is eta equals to minus infinity. So this is r equals to constant lines. These are eta equals to constant lines. And I'm assuming some gravitating source along this line AD. Okay. Now, then ask the same question, how to understand linearized gravity in this background, but in conformal coordinate. Because now I want to solve the equation in terms of inhomogeneous solution in terms of T mu nu. Then what you do, you just follow what you just do in the usual textbook. So you just write down the equation. This is just a linearized gravity prescription. What we do in flat space, you just linearize the Einstein equation in terms of flat metric, then you obtain a wave equation, then try to solve this wave equation in terms of Green's function. Then once you use the conservation equation, you can write down this d3x Tij in terms of quadrupole moments. So can we just follow this step in de Sitter? So the answer is yes. So if you do that, but you need to work a little bit hard, because you have to choose a really right gauge condition to make the equation decoupled, because a priori it is not clear whether these equations are decoupled in de Sitter background metric or not. So I can just write down the wave equation in terms of this background metric. So I can compute all the covariant derivative in terms of this background metric. And I can define this new kind of variable and this new gauge. So this is not exactly Didonder, but it is, I mean, this gauge is first used by these people. And they show that in terms of this variable, chi hat, chi 0i, chi ij, you will get decoupled equation. That is important, actually. So priority is not clear. So because the equation comes in a coupled way. So then, so these chi ij's are the physical field. So now you can ask whether I can solve this chi ij in terms of Green's function. Okay, so just like here. And again, the answer is yes, but the solution is a little bit non-trivial. And then if you look at the Green's function of this differential equation, they have a delta term and a theta term. So this delta term basically says the propagation is along the light cone, but the theta term represents that you can have a scattering in the, because your background is curved. So as the wave propagates, it has some scattering, but these terms are absent in flat space. Actually, if you just look at the linearized case, you have only delta term in the Green's function. And this is a consequence of just curvature of the background. And this also amounts to a tail term, which has a integral from -infinity to eta retarded time. So if you look at the eta is here, in the eta is -infinity is here, and to the retarded time. Basically, this integral tells any point of the field at any point don't only depend on the retarded time, but it actually depends on the entire history of the source. So this is kind of a tail term you also get in a higher order PN calculation actually. But for the de Sitter, it appears on the leading order because your background is curved already. You are starting with a curved background itself. Okay. Now I can just ask how to write down this d3x Tij solution in terms of moments. Okay, so for de Sitter also, you have to define your moment really carefully because you expect that this integral should be coordinate invariant. So you have to define this in terms of some tetrad variable. So you choose a frame on the de Sitter background. Then you just, this bar index are just frame index. Then you can just convert this tetrad frame in terms of coordinate frame. Then you will get automatically some scale factor of de Sitter. And this is the mass moment. So this is like T00 xi xj, and this L index like is a multi-index. So if I say xi xj, that means this is qij. So if it is xi xj xk, this means qijk. So this is just multi-index. Okay. So for our purpose, I think it is enough to just consider this two index qkl, which is for the mass moment, it is T00 xk xl. And for the momentum moment, it is defined on T0I, and this is stress moment. And also you notice this, we define a pressure moment, which is stress of Tij. Okay. Now the interesting thing, what happens in de Sitter, if you try to relate this d3x Tij, so if you remember, my goal is to relate this d3x Tij in terms of moments. Okay. So if you try to relate this d3x Tij, you will appear there is a term which depends on Qij p. Okay, but if you look at, and also it appears with the cosmological constant. And if you look at the structure of Qij p, it is exactly Tij xk xl. So it has 2 order more xk xl, but it is with the trace. Okay, and this makes the computation really non-trivial. And so look at this d3x Tij. So let me just show you this one. So basically we want to compute this integral, right? d3x Tij in terms of moment. Then I can just do a Taylor expansion. What we usually do, I can do this Taylor expansion. This 1 and 2 is just with respect to derivative. But this conservation equation basically tells you the d3x Tij depends on Qij p. Okay, but Qij p has a structure of Tij xk xl. Now, if you look at the higher order term in the Taylor expansion, this term, so this term has the exactly same structure, Tij xk xl. So this has 2x. So that means in de Sitter, this higher order term is actually connected to the lower order term. And you can show they contribute exactly to the same order. So that means you cannot just truncate this series to the leading order. So if you want to really take care of all this term, that you have to take care of this term. So this was actually one of the missing thing, what Abhay and one of my PhD work also. So we just consider this leading term, But we realized that you have to add this higher order term to include all L equals to 2 mode. By quadrupolar mode, I mean that if you just give me a solution in terms of partial wave expansion, so quadrupolar mode is up to L equals to 2 mode. And this makes, actually this conservation equation, which connects via Qij makes de Sitter non-trivial. So that means you need to take care of this higher order term. And we also define what is the quadrupolar truncation order, namely if your this index greater than 2, you just truncate that. And from the conservation equation also you can show that these quantities are 0. Okay. So now if you take care of all this, then again, so my main goal is to write down this mass loss formula of boundary variable, but I want to write in terms of moment, because this moment moment captures the information of the retarded solution. That is important. So then you just do a coordinate transformation. This coordinate transformation is also non-trivial. So you go from boundary gauge to harmonic gauge. Then you do also one more coordinate transformation, which just transform this all this Hij in boundary gauge. Then you can just relate what the boundary variables are written in terms of moment variables. Okay. So once you do that, then you try to ask. So this is my first boundary gauge fixing mass loss formula. You try to ask what happens to this formula if I just write all these variable in terms of moment variable I just shown. Then a priori you can just massage this formula in a way such that this right hand side is positive definite. Okay, so now I am defining this QDE with this horrible looking terms. I mean, there is a reason why we guessed this term. And you can see this term has a good lambda goes to 0 limit. This reduced to m. You can show this xij actually goes as order h square. So these xij actually are part of boundary gauge fixing. So as I said, so for this, to get this answer, I use this boundary gauge fixing such that delta UA0 is 0. And this is part of boundary gauge fixing. You can show that this term goes as order h square zeta. And this zeta also got order h square. So all terms are 0 actually if I take h goes to 0 limit. So it gives you good limit for lambda goes to 0 limit, but we don't know how to interpret this term on this left hand side. Okay.
Can I ask you, so these extra terms,
Yeah.
so should I understand them as the fact that since it's the background is curved and there's expansion, even if there is something small happening far away from me, it gets amplified over time more than in flat space, and so I'm going to see more of the source? Should I think of them as higher modes in the expansion of the structure of the source, or just as higher effects?
No, it is just effect. I mean,
It's just effects, so it's not sensitive to the internal structure of the source.
Yeah,
I see.
Still, but yeah, I mean, this left hand side we don't understand, but as far as our solution is concerned, it is up to L equals to 2 mode. So if you just
okay.
That is I think that is completely fixed. So our solution is L equals to 2 mode. But what we did, I mean, just looking for a formula for that such that this right hand side should be negative definite. Okay. So and I think this is one way to write that. So then we found, so you can write this formula in a other interesting way actually. So you can just write this identity in terms of this variable. And then you can again write a positive definite formula in terms of this Rij. I mean, there is a reason why we wrote in terms of this Rij, because our previous formula is written in terms of this Rij field. But as I showed, that doesn't take care of all the Qij P term, that pressure moment term. But this Rij is exactly same as their Rij in terms of rho, but they have some non-trivial term for Qij P. So this Rij expression actually exactly match with Qij rho, but doesn't match with Qij P coefficient because of this higher order contribution to the Taylor expansion to here. Okay. So once you corrected that, then this is the upgraded formula of Ave and one of my PhD work. And then again, you can write down this mass loss formula in terms of this Rij. And again, it is positive definite. So this E is even part and O is odd part, so that details is not important. So Well, so also Bonga, Boonstar, Perez write down a energy flux formula, but what they did L equals to partial expansion of homogeneous equation, and look at what is the energy up to L equals to 2 mode. So their expression is this one. So you can think of this AM as a coefficient of L equals to 2 even parity solution. So you give me the homogeneous equation, then I can just solve till L equals to 2, and I can write a expression for energy. Now the question is how their formula actually related to the previous formula I have shown here. So I can you can achieve that. So we wrote a paper with Amitabh and Hers and Shitender. So where we construct some solution like de Sitter Tucholsky wave solution. Tucholsky wave solutions are actually useful to understand some numerical relativity. We just construct some Tucholsky wave solution in de Sitter, and from this Tucholsky wave solution, we relate how this Bonga Boonstar Perez solution is related to de Sitter Tucholsky, and also our solution with Geoffrey. But if you remember, these two solutions are in a different boundary gauge fixing. But once you identify this formula, this one is reduces to exactly the formula I previously showed. So this result is also important because Bonga's formula, Bonga Boonstar Perez formula, is obtained in a different boundary gauge fixing. But from their boundary gauge fixing, we have shown then this formula is also mapped to our formula, but our energy loss formula is obtained in a different boundary gauge fixing. So at least this flux formula is invariant up to this boundary gauge fixing. So that statement is important. Okay, so here is the summary. So there, as I said, there are two distinct proposals of energy loss in de Sitter, but these two have exactly the same flat limit. So one proposal is this one in terms of Rij, then other proposal is you can write it in terms of this factor. So it has both of this formula has a exact same flat limit, and yeah, so this is upgraded of Abhay's formula and our formula, correcting the pressure moment term, and matching with Bonga Boonstar Perez result. It shows that it at least the energy flux formula right hand side is invariant under the interesting class of boundary gauge fixing, but it still doesn't prove the full gauge invariance. I mean, you can write down the one more solution which can be positive definite. You can just come up with. I don't know, but yeah, I think one of the and also we didn't able to show this mass loss formula in terms of boundary variable, just like whether there is a negative definite mass loss formula or not. I mean, one of the missing link might be we still don't understand how to impose no incoming radiation in boundary variables. Yeah, I will just leave it here. Then I will just take a question. Yeah, I just so.
Questions?
Sorry, it's more a comment than a question. You know, when you're working with different, you know, comparing things in different gauges, within the context of holography, one thing that's proved to be quite useful is to work with perturbations where one explicitly builds in the possibility of gauge covariance. So this was done, for example, by Costas and myself in the context of Kaluza-Klein holography. So you start from, in a sense, your preferred gauge, and then you build in sort of gauge invariant combinations of perturbations. I mean, this has been done partly in a cosmological context as well, you know, where you inherit it from analytic continuation. It hasn't been done in this context.
Yes, but yeah, I'll make a comment. So you can write down what we have shown the energy formula. You can write in terms of this boundary quantity, in terms of this TAB, or even if in terms of electric part of while. So I can just write down on the boundary data. So I can just write the expression, which is like EAB, which is on the boundary, and some delta GAB. This I can do. I mean, because this is just TAB and the Lie of Jai. I mean, I can just write it like that, right? So then I think, yeah, so I can write my energy flux formula in terms of electric part of while and completely on the boundary, and also the linearized perturbation in the linearized theory. And I think Bonga Boonstar Perez also started from this equation, but showing that this equation is exactly so. Basically, I can write down this kind of formula also in terms of electric part of while. But showing again, this is negative definite. I mean, it is now obvious. So I can just expand this quantity in terms of linearized field because it's a linearized regime. So I can just expand this AB in terms of linear field. So this is already my linear field. So then try to understand whether this quantity is again a negative definite or not. My understanding is that no. So they also started with this formula. Then they try to massage all this thing. They came up with this formula, which they say that this is my energy flux. I mean, yeah. So if you start with this one also, my point is that this is, you cannot show this quantity itself in the linearized context is negative definite. That's my comment. I think I checked that.
Well, maybe in that regard, I might add perhaps this formula. I mean, I know we already discussed, but just to point it out of the superpointing of Zenovi, that's completely gauge invariant, right? Because you compute the Bell-Robinson in bulk.
Because that is also written in terms of electric part of while. You can write electric part of while. I mean, I think this formula is also started from electric part of while. I mean, it is worthy to check, but I'm not sure whether that is again negative definite or not. I mean, absolutely one can check that, pointing this PMU vector, whether that can give at least some hint on no incoming radiation or not. That worthy to check. Yes, that I agree.
Yeah, I'm not sure I followed at the end because you went from bounded and you went to the Donder gauge, then conformal, and then backwards. And at the end, how did you extract your quantity, which I understood you liked for some reason because it had. No, I think it was before. You said, yeah, this thing. Yeah. You said it has a good flat limit, and that's why this is.
So our goal is that we just want to write down something positive definite here. So we want this flux formula should be negative definite. That is our goal.
Yeah.
So then I said that we still don't know how to impose no incoming radiation in Bondi.
Yeah.
Just go to this, write the solution in terms of Qij, because at least that has some information of retarded Green's function.
Mm-hmm.
At least, I mean, if I just write down visitor, so at least if I just construct my source here, so at least at least in this harmonic gauge, at least the solution are constructed in terms of this retarded solution. Then what I did, I just go from this Bondi-Sachs coordinate to harmonic coordinate. So I just do a gauge transformation from this background metric of harmonic gauge to Bondi-Sachs. Then again, you need to do some gauge transformation so that this perturbation are also in the Bondi gauge itself. So namely, in Bondi gauge, these terms are zero, right? Delta RA and GRR is zero. So you need to also impose that one for the harmonic gauge solution. Once you do that, then you can relate all your Bondi variables in terms of moments. So I'm just going a coordinate transformation from Bondi gauge to harmonic gauge and putting all this harmonic field in Bondi direction. Bondi's this Bondi frame.
Yeah.
Once you do that, then you can relate all this quantity in Bondi variables, CAB, QAB, all this quantity in terms of all these Qij variables, because these are my solutions. So I can just do a one-to-one mapping. Then I just substituted this solution here, nothing else. And then my comment is that I can just write this solution in terms.
And why this one in rather than the other formula? You had two formula of this kind, right?
At first we arrived that, then we realized if I just redefine this in terms of Rij, because this actually done by Avoy, but they have this Qij are different. Because as I said, so this Qij actually mixes the order, mixes the leading order term with the higher order term in the Taylor X function. So in their X function, these Qij terms are wrong, but Qij rho exactly matches. But I can write this identity in terms of, again, this quantity with a total derivative. Then I can just shift this total derivative to the left-hand side to get, again, a positive definite flux formula. So my conjecture is that we have two negative definite energy flux formula. We probably don't know what is the gauge invariant thing, but at least we have also shown it is invariant to this boundary gauge fixing. So boundary gauge fixing in terms of this boundary coordinates.
I might need further.
Okay, we can talk.
Yeah.
Yeah.
Other questions, comments, observations, debates? No. Okay, well then let's thank Jahanur again.